other thing that gets used quite a bit in optimization is something called a directional derivative. So a direction in a preferred direction, right? So okay. So when I say directional derivative, I have to supply you with a direction. So let that direction be given by the symbol P. Okay. So before I go into the definition, let's get a geometric picture. What we're saying, rate of change of the function along the direction P. That is the meaning of directional derivative. Okay. Again, the definition is very intuitive, right? Take the function value along the direction P by making a small epsilon change and take the limit. That's all there is. So if I am at x, I need to go some small distance in the direction P. So how will I write that mathematically? Okay, something simpler. Projection was what was said. I want to denote a small walk along the direction P starting from x. How will I write that? X plus some small number times P. Will it do it? It will do it, right? So this is the picture. Supposing this is the origin, this is x over here, this is the direction P. Okay, P typically will be specified by a unit vector, so it will have unit length, but I don't want that. I want a small distance over here. So I'm going to define this as epsilon times P, small vector over here. So this is going to be x plus epsilon P minus what? F of x divided by what? Epsilon, obviously limit epsilon tends to 0. Okay. Yeah. I'm going to take P to be a unit vector. Okay. Typically, when I say direction, I would specify it in terms of unit vector. Okay. So the symbol for this is written often like this. Now this has a simple form. When f is we say that when f is continuously differentiable, you can show that there is a nice form for this. Can someone think of a geometric way of understanding this? This is written as grad f transpose P. That is correct. So when I say when we talk about grad f, we have already thought of it as a column vector, right? Column vector has an algebraic picture, means collection of n numbers. That has no geometry in it, but you can also visualize it as a vector with n components. Now in n dimensions, what does the dot product translate to? Transpose, right? A transpose B is the inner product of two vectors. Now what am I doing? I am taking, so to speak, the inner product of two vectors. One is the direction and one is the rate of change vector. So I am saying, what is the rate of change along direction P? Give me the gradient, I am going to project it onto P. So that's the geometric meaning over here, right? So if, for example, a function was not changing in one direction at all, right, and I ask you what is the rate of change in that direction, it's 0, but you can see also graphically how that will be the case, right? Okay. Okay, so I think the final couple of things is one is just a definition, which I spoke about at the start, which is the generalization of second derivative, which is called the Hessian. Okay, Hessian matrix, which is essentially a matrix of second derivatives. Okay, and let's for simplicity take f is Rn to R, so scalar value. Yeah. Yeah, by finding a perpendicular direction to, yes, this will get used shortly. Okay, right. So this is also written as del 2 f. Okay, and all the mixed derivatives also appear. Okay, then this and so on. Okay, this will be del 2f by del x2 xn. Okay, so the diagonal terms contain the pure double derivatives. Okay, this I mean straightforward generalization of single variable calculus. Okay, we will use this when we start talking about Newton methods in optimization. Okay, but because there are second order derivatives, we have to first go over the methods which use the first derivative, right? As we mentioned in the start of class, gradient descent, it will use only the first derivative. Okay, as you can imagine, the math is much easier when I stay at first order derivatives. Second order derivatives we can deal with, again we have to be patiently working through each dimension and so on. Now the last point for today is the mean value theorem, extremely important theorem. Okay, again we'll start with the revision of one variable calculus, right? So if I had f which was going from R to R, right, and I have x comma y belonging to R such that let's say x is smaller than y, then what is the short form for this is MVT. The MVT states that f of y is f of x plus what? This, okay, hint, it will look a little bit like Taylor's theorem, but not quite. There is a y minus x, right? And what? The very precious term over here, f dash of not x. If I write x, I am writing the first order Taylor approximation, but I am writing equality over here. Some z over here, z belongs to x comma y. So this is not approximate, this is exact. So what is it saying is that I can tell you the value at a point y exactly if you can if allow me to use the derivative at some intermediate point z. Okay, so this is not an approximation, this is exact, right? But the trouble is I don't know what z this is. So that's what you have. Now if I want to extend this to f that is going from Rn to R, right? So y is some point a little further from x. So I'm going to generalize it over there. So I'm going to write this as f of x plus p. Okay, the first term will be, if you were defining it, first term you would write as f of x. Very good. Okay, second term what would you write? We know that f dash is going to get replaced by grad, right? So I'm going to write grad f over here. Okay, and z was some point between x and y. So in this case between x and p, right? So the way to write this intermediate point, again very simple geometry, I will say x plus alpha p. Okay, alpha is a scalar. If I say alpha lives in 0 comma 1, okay, in fact, right? So as it tends to 0 I am at x, and as it tends to 1 I am at x plus p. So I am going from starting point to ending point. What should I multiply it by? I had y minus x. In this case, y minus x would be p. This is nearly done. There is one missing bit. There has to be a transpose for it to be a legal multiplication, right? Right. So this was my x. This is my p. This is my x plus p, and this can be my length alpha. So this is x plus alpha p. Okay, so that brings us to a conclusion of the review of calculus, right? So I'm sure you are seeing many of these things for the first time, right? How do we generalize starting from scalar to a vector case? And in all cases, there is no great fireworks or magic happening over here. You're just extending in dimensions, right? And doing the calculus properly, right? So everything that we looked at, we started with defining the derivative, right? We took a very intuitive definition. We started with our high school definition, just simply generalized it to the vector case, and that gave us the gradient, which is a column vector. It's called the Fréchet derivative, right? Then we looked at what happens if the function is not a scalar function but a multivariate function, right? That is, it's not just fx but f1x, f2x, fmx. Then the gradient became the Jacobian. Then we looked at the generalization of the chain rule, right? We took a simple example to put this chain rule into practice. Then we looked at one object that we call the quadratic form. Okay. Later on, we'll see this quadratic form has very nice geometric interpretations. It look like a cone and various such objects in n dimensions. And we proved its derivative. I mean, rather, we found its derivative to be a very simple expression. Looked at the directional derivative, and after defining the Hessian matrix, I looked at the mean value theorem. So if you look at the lectures on the class website, there's many places they will have some extra proofs, some extra examples. So you can go and have a look at that to brush up your understanding. Okay. Can you pass the chits around? Oh, you pass it. Okay. So open for questions. We are not we haven't parameterized it in some sense. I mean, I'm talking about like the choice of x and p are arbitrary. So there's no parameterization there. What has been parameterized is how do I travel from x to x plus p. That is what has been parameterized. It's a straight line between this, and that is the theorem. That is the statement of the mean value theorem. No, p is my choice. P could be anything. It's up to me what I want to choose. So it's not given to me, right? So in some sense, you can think of it like in the mean value theorem for scalar case, I gave you a x and a y. In this case, I'm giving my y is simply x plus p. So I could have rewritten this thing in terms of x and y also, the same idea. Give me a start point and an end point. I will tell you the value of the function using some point in between. Yeah. Yeah. So I mean, in practically, what is it saying? Supposing I have some point x over here, it is saying that the value of the function over here can be determined in terms of the value of the function here, plus you can interpret this as a directional derivative, right? So in that sense, this is like a directional derivative over here, which will give me the value of f of y. Right? So by the way, the proof is not very straightforward. So the class website has a derivation, I mean a link to a derivation which you can look at. The Hessian matrix, yes. Why does f have to be continuously differentiable for this to happen? Again, I'm not going to prove it rigorously over here. There is a certain requirement over there, because what was the definition of continuous differentiability? That the derivative itself was continuous, right? It's not very obvious just looking at this definition why that should hold true, but it follows from rigorous derivation. So yeah, if I can share a derivation with you if you want, but then everything gets expanded if we start including that. So to kind of give you some sense of the question at the start of the class, why does ML and related things only do gradient descent? Why, for example, no one really talks about Hessian over there, because your n in the case of data science problem, for example, can be very large, 10,000, 1 lakh, 10 lakh, right? Derivative itself is hard to compute, and then second derivatives, right? So it becomes computationally very, very challenging. So you do the simplest possible thing. But that is high dimension data science. A lot of engineering is not that, and over there you should use second order methods. Right? Any other questions? Actually, that is one of the things I'm keeping in this course, that I don't want to fall into the trap of only talking about things which are of interest to ML, because the whole world is not ML. There's a lot of engineering where you cannot do ML, conventional stuff, where you need, for example, second order methods and all, where we will need these Hessian things, right? Not everything should be done as with first order stuff. If you can get quadratic rate of convergence, why would you settle for first order rate of convergence, right? So you learn more tools, so you have more things in your toolbox to apply. That's the basic idea. Okay, so if you have no doubts, you can hand us your feedback sheet, and I will see you tomorrow.